In our last video, we started looking at the alkylation of enolates, and we started with C, direct alkylation of enolates. In this video, we'll be looking at another approach toward the alkylation of enolates, and this is called the acetoacetic ester synthesis. But before we move forward with enolate alkylation, there is one other important reaction that we need to look at first, and this is a reaction of beta-keto carboxylic acids. Now, if we have a regular carboxylic acid and we heat it up, we get no reaction. So this reaction that we're looking at is not common to every carboxylic acid, only to a carboxylic acid that alpha beta to it has another carbonyl. As long as we have one carboxylic acid, then alpha beta to it, this could be an aldehyde or a ketone or an acid or an ester. So there's a variety of structures possible here, but this one has to be a carboxylic acid. So when we have a carboxylic acid that has a carbonyl beta to it, and we heat it up, what we're going to get is this. So carbon dioxide is given off as a byproduct, and we have basically carried out a decarboxylation. So we've lost CO2 from one of the, in this case, from one of the carboxylic acids, and this hydrogen, we can think of it as if this hydrogen is now connected to this carbon. How does that work? So let's write our beta-keto acid like this. Here's a CH2, C double bond O, and then this is the OH over here. So one of these has to be a carboxylic acid, and then alpha beta to it, it doesn't matter if it's a carboxylic acid as long as there is a carbonyl. This undergoes a pericyclic reaction. So remember when we talked about Diels-Alder reactions, that was a special set of reactions that go through a cyclic transition state. Well, that's what we have happening here. Where it starts from doesn't really matter. Let's think about if this set of electrons could share electrons with this proton, that would push these electrons here between the carbon and the oxygen. That would push these electrons this way. So what does that give us? From the top right, we have CO2. I'm drawing it bent just because that's the way that we were here, right? So from this piece, we get carbon dioxide. This is what's given off. And now what do we have here? I'm going to write this one below. So we have a CH2, now double bonded to a carbon that's still connected to an OH. That carbon is single bonded to an oxygen, which is single bonded to a hydrogen. So that's a weird looking compound, but what you should notice is that this is an enol. So what we have here is the enol form of a carboxylic acid. So this enol will equilibrate to give this carboxylic acid. So this is now the methyl group, this carbon is now the carbonyl, and this OH didn't change. So this is what happens when we have a decarboxylation of a beta-keto carboxylic acid. Let's look at a couple more examples. Let's focus on this carboxylic acid. This is the alpha position, beta position, gamma position. So we have a gamma keto. This will undergo no reaction. If we look at this one, focus on this carboxylic acid. This is the alpha position, this is the beta position. We do have a carboxylic acid with a beta carbonyl, right? Just a reminder, beta keto carboxylic acid, it doesn't have to be a ketone. This is another way of saying a beta carbonyl. So we have our carboxylic acid, alpha beta to it is another carbonyl, so this can lose CO2, and that will give us this carboxylic acid, and we now have a hydrogen here. And then one more example, I'm going to draw it this way. Here is our carboxylic acid, alpha, beta to it. We have a carbonyl that's part of a ketone, and so this, when heated, will also undergo decarboxylation. And so we're going to lose this CO2, and notice we already have one hydrogen here. What we will end up with, we now have two hydrogens over here. So any carboxylic acid with a carbonyl beta to it can undergo decarboxylation when heated. Why would we want to do this? We're breaking a carbon-carbon bond, we're making our molecule smaller, so what is the advantage of this reaction? Well, notice if we look at our product, we have a ketone, and our starting material was a ketone with a carboxylic acid beta to it, which means we have this position that's alpha to both groups, which means this can be alkylated more easily than what we had over here. The purpose does seem a little strange when we're looking at a very complicated way to make acetic acid, for example, but thinking about the fact that this reaction can happen, on the next few slides, we're going to be looking at some applications of this, how this can enable us to carry out a more difficult alkylation. On this slide, we have an example of the acetoacetic ester synthesis, which involves alkylation followed by saponification, ester hydrolysis, and then decarboxylation. It's called the acetoacetic ester synthesis because one prime example is using this compound as a starting material, which is commonly referred to as acetoacetic ester. This one in particular would be called ethyl acetoacetate, for example. Notice what we have is an ester, and then alpha beta to it, we have a ketone. This can be treated with a base. We still pick an alkoxide base that matches our ester. This is going to pull off one of these protons, giving us this enolate. I'm just going to use ET for the ethyl group. Now, this enolate can carry out an alkylation reaction, or it can do an SN2 substitution, where this is the nucleophile and it shares its electrons with this carbon, pushing away the iodine as a leaving group. And that gives us this compound, where we have now alkylated the position in between the two carbonyls. Next, we can saponify, so we treat it with base to give us the carboxylate, and then aqueous acid workup will give us the carboxylic acid. So we get the CH3, C double bond O, CH, C double bond O, OH, where this C is connected to the alkyl group. And then finally, when this is heated, we have a beta keto carboxylic acid, and so this can undergo decarboxylation, which will give us CH3, C double bond O, CH2 connected to the CH2, CH3, where carbon dioxide is given off as a byproduct. Here we can see this again written out kind of shorthand, and we start out with our beta keto ester. This is treated with base followed by an RX, and then the ester is hydrolyzed, and then the carboxylic acid is heated up to undergo decarboxylation to give us this product. So let's look at this more closely. From this piece, we get this, where an alkyl group has been connected. From the perspective of the alkyl group, here's our alkyl group, and so it's as if we put on an acetone onto the alkyl group. So looking at it from the perspective of the Rx, our R group has this group added to it. So with the acetoacetic ester synthesis, the overall transformation is that we are replacing an X group with basically acetone. So we can do this by the acetoacetic ester synthesis, where we start out with this beta keto ester, base, and then the alkyl halide, and then we alkylate here. We hydrolyze the ester to give the carboxylic acid, and then we heat it up to decarboxylate, giving us this product. Well, a couple slides ago, we saw that if we had acetone and we treat it with LDA, then we can deprotonate either one of the alpha positions, and that would give us as an intermediate this enolate. Now once we have this enolate, if we add in some ethyl iodide, this could do SN2 substitution, and that would give us this compound, which is the exact same thing. So why would we carry out a reaction that takes 3 steps when we could carry out a one-step reaction? Well, in this particular case, maybe we wouldn't do that, right? This might be the better way to go. But there are some problems when it comes to direct alkylation of enolate ions. We're limited to ketones because aldehydes can undergo different types of reactions. We are limited to symmetric ketones because we can't always control where an unsymmetric ketone would get alkylated. So there are some issues that can be overcome with the acetoacetic ester synthesis. But furthermore, with the acetoacetic ester synthesis, there are some other extensions that make this a better approach than direct alkylation for certain target molecules. So here's another example, and we can carry out the acetoacetic ester synthesis on other beta keto esters. So let's say we are starting out with this compound. We treat it with, because we're using a methyl ester, we're going to use methoxide to pull off a proton from here. That enolate will then attack here and do an SN2 reaction. So that will give us this compound. When we saponify, so step 1, when we treat this with hydroxide, this is actually going to give us the carboxylate. So this is why we have to include the second step of H3O+, because this oxygen can grab off a proton so that we get this compound. And then finally, when we heat it up, we can drive away carbon dioxide. And so we're going to lose the carbon dioxide from here because alpha beta to it, we have a carbonyl. So we will get this as our final product. In other words, by carrying out the acetoacetic ester synthesis, whether it's on acetoacetic ester itself or any other beta keto ester, we can basically alkylate alpha to any ketone. It's just that we're not starting with a ketone, we're starting with a beta keto ester. Okay, once again, why don't we just use this and treat it with LDA followed by ethyl iodide, and that would give us the same thing, right? Well, with this example, it still isn't crystal clear why the acetoacetic ester synthesis approach is better than the direct alkylation. I probably still haven't convinced you of the usefulness of the acetoacetic ester synthesis, but bear with me. So once again, we've got alkylation, saponification, decarboxylation. But another extension is that we can do dialkylation, so we can alkylate twice. So if we start with this compound and we treat it, notice we have the ethyl ester, so I'm using ethoxide. This will grab off a proton from here to form the enolate, and then that enolate will act as a nucleophile, attack here, push out the I- as a leaving group, and at the end of the first arrow, we will have this compound where we've connected an ethyl group. Now, this can do it again. Treatment with another equivalent of ethoxide can grab off this proton, forming the enolate that can then act as a nucleophile, attack here, push away the I- as a leaving group. After the second arrow, we're going to have CH3, C double bond O, C, C double bond O, O, E, T, where that central carbon is connected to the CH2-CH3 group from the first alkylation and the CH3 group from the second alkylation. Next, this will undergo saponification so that this is converted to the acid, and then this will undergo decarboxylation, and what we end up with after a few more steps, we have this from the first alkylation and this from the second alkylation, and we got back a hydrogen at the end. So, could we have done this by direct alkylation? From here, if we treated it with LDA followed by ethyl iodide, then sure, we could make this. But if we tried to alkylate a second time, we are not going to exclusively alkylate at this position. We might alkylate at this position, which is going to give us a mixture of products rather than one product selectively. So in this case, we cannot make this target by direct alkylation starting with a small ketone. And so extra steps are necessary to give us our target product selectively. This concludes your introduction to the acetoacetic ester synthesis. We will be looking at some examples so that you can get more practice applying this. It will be important for you to think about what targets can be accessible through direct alkylation and what targets require the acetoacetic ester synthesis to be able to make them.